Welcome to my first video lecture on the concept of vector spaces. As we all know that there are two types of physical quantities we have learnt in our primary schools. One is called as scalars and the other vectors. We know that scalars are described by magnitude alone, and vectors, along with magnitude, they need one more thing called as the direction. Now, when we talk about vectors, the first thing that comes to our mind are these directed arrows. This is true. In terms of physics, we can represent vectors with the help of these arrows because this gives us the magnitude as well as the direction. But for a mathematician, from the point of view of mathematics, for us, we will be treating everything as a vector. Everything under some condition. Let's see what the conditions should be. So for any element to be a vector, it should belong to a special set called as a vector space. And what do you mean by a vector space? Let's see. So a vector space, let us call it as V, is a set along with two operations plus and dot. They are called as vector addition and scalar multiplication. So a vector space V is a set along with two operations, vector addition and scalar multiplication, that satisfy a few properties. Okay, let's see what the properties are. That satisfy the following properties. Okay, so let's begin. The first properties, I'll be listing down 10 different properties. Among the 10 different properties, the first 5 properties will be for vector addition and the remaining 5 properties will be dedicated for the scalar multiplication. So let's look at the first property. So I'll use different color. So say this is for addition. The first property should be that addition is closed, and it's called as the closure property. This simply means that whenever you take any two vectors, say v1, I should say element because they are not yet eligible to be called as vectors. So whenever I take any two elements, say v1 and v2 from the set V, the addition of these two elements should also belong to the set V. I should say the sum of these two elements should also belong to the set V. What is the second property? The second property is called as commutativity, which simply means that it doesn't matter you do v1 plus v2 or you do v2 plus v1, it's the same. So v1 plus v2 is same as v2 plus v1. This is also true for every v1 and v2 belonging to the space V. The third property is one of the most important properties, and it's called as the existence of zero, which means that there should exist a special element called as the zero vector belonging to the space V. This is simply a notation. The zero V is simply a notation. It could be anything from the vector space, from the set V. The speciality of this element is whenever this is added to any element of the vector space, it has no effect, which means that it will be simply equal to V. So you have V plus the 0 vector same as V, which is equal to the 0 vector plus V. The fourth property for addition is the existence of the additive inverse. What does this mean? This simply means that whenever you have any vector CV belonging to the vector space, you can always come back to the original position that from where you started, which means that you can always have another vectors, let's say V dashed belonging to V, such that after V, if you trace V dashed, you come back to the original position, which simply means that it's equal to 0V. This simply means you have a V, you can come back to where you started by adding this V dashed. So we can think of V dashed as minus of V, but yet minus of V has no meaning until we define it. Okay, so now this gives us only 4 properties. Let's see what the 5th property is. So the 5th property is called as associativity. This simply means that whenever you take 3 different vectors, of course this has no meaning. When I talk about addition is binary. You can have only one vector on each side of the addition sign. So when I talk about this addition sign, I've got 2 vectors. So this does not have a meaning. To give it a meaning, I'll have to write something like this. This means that I do this operation first, that is V2 plus V3. I know that this gives me another vector in the space V. This vector can be added to V1. It will give me another vector. But what if we do V1 plus V2 first and obtain a vector and add this to the vector V3? We are saying here that these 2 vectors will be the same. That's associativity. And this should be true for every vector V1, V2 and V3 belonging to the space V. Now this accounts for the properties associated to vector addition. So please remember that there are 5 different properties for vector addition, starting from closure, commutativity, existence of 0, existence of inverse, and the associativity property. Now let's talk about the properties related to scalar multiplication. We'll call it as SM1 to 5. Okay. So as we had in the vector addition, the closure property, we have in the scalar multiplication a closure property. And this would simply mean that you take any vector, multiply it with a scalar, you'll always get another vector in the space V. You take any element in the set V, you scalar multiply it with any number alpha, you get another vector, another element in the set V. This is true for every scalar belonging to the set of scalars called as the set of real numbers, and for every vector V belonging to V. That's scalar multiplication. Okay, let's talk about the second property of scalar multiplication. And the second property for scalar multiplication is the distributivity property. So distributivity of scalar multiplication over vector addition. What would this mean? This will simply mean that you take a scalar, you multiply it with a sum of two vectors. This is same as you stretch the vector v1 by alpha. You multiply the vector v1 with the scalar alpha and you add it to another multiple of v2 by the same scalar. So this simply means that alpha can be brought inside. So alpha times v1 plus v2 is equal to alpha v1 plus alpha v2, and this is true for every alpha belonging to the set of real numbers and for every v1 and v2 belonging to v. Now let's talk about the third property of scalar multiplication, which is another version of distributivity. But this is distributivity of the usual plus over scalar multiplication. Now what do you mean by the usual plus? When I say usual plus, it simply means the plus that we have studied in our childhood, that is 2 plus 3 is equal to 5, 5 plus 7 is equal to 12 kind of. So we have different kinds of addition today. As we saw today, that there is something called as vector addition. There are different types of additions. So that's the reason I have to use the word usual plus. Okay, what would this mean? This simply means that if I add two scalars with the help of this usual plus, and if I multiply, you know that when you add two scalars, you again get a scalar. When I multiply this scalar with a vector, it is same as multiplying the scalar alpha with the vector v and adding it to another multiple of v by the scalar beta. So here I am simply saying that this is being distributed inside. So alpha times v plus alpha times v plus beta times v is same as alpha plus beta times v. And this is true for every alpha and beta belonging to the set of scalars, set of real numbers, and for every vector v belonging to v. Let's talk about Now let's talk about the fourth property of scalar multiplication, which is the associativity property again. So what would associativity mean here? This will simply mean that alpha times beta times v is same as alpha times beta times v. This is true for every alpha and beta belonging to the set of scalars and for every v belonging to v. Which means that if you have a vector v, you stretch it by alpha beta scaling factor. This is same as stretching the beta times v by the scaling factor alpha. Okay. Now let's talk about the last property of scalar multiplication, which is the effect of a very special number in the set of real numbers, and that is 1. So what would happen if you have 1 times a vector? You guessed it right, it will have no effect. So 1 times v will be same as v, and this is true for every v belonging to v, which means that it is also true for the 0 vector. Okay, so here we saw that there were different objects that had come into picture. What are the objects? Let's list them down. We talked about a set v. We started with a set v. We talked about the set of real numbers. There was another object called as the vector addition that had come into picture, and another object called a scalar multiplication that had come into picture. So how do you cook a vector space? So you take a tumbler, which is V. Of course, pour some elements into it. Those are our elements V. Okay, and you add vector addition and scalar multiplication into it. You get something called as a vector space, provided the 10 properties are satisfied. Since R plays a very important role over here, we will call such spaces as vector space over R, that is the set of real numbers. Okay, so let us look at a few examples of vector spaces, and we will also look at a few counter examples of vector spaces, a few sets that cannot be identified as vector spaces, cannot be qualified as vector spaces. So the first very famous example of a vector space is the space Rn, which is also called as a Euclidean space. What do you mean by Rn? Rn is simply a collection of n tuples. N tuples mean you have n coordinates for a point in the space, and each of these coordinates xi belong to the set of real numbers. For example, R2, which is also called as the xy plane. Every point in R2 will have two coordinates x1 and x2. Now, how do you add two elements in R2? What does it mean to multiply an element of R2 with a scalar? I mean, what is vector addition and what is scalar multiplication in R2? So let us see. You can define, let me use some other color. I can define the vector addition plus as x1 comma x2 plus y1 comma y2 is equal to x1 plus y1 comma x2 plus y2. What would this mean? If I have x1 comma x2 and if I have some, say some y1 comma y2 over here, what does it mean to add these two vectors x1 x2 and y1 y2? So as we know that this will simply give us a new vector, and this will be our new vector, which is x1 plus y1 comma x2 plus y2. This is also called as the parallelogram law of vector addition. Wow, how would scalar multiplication look like? So you can define dot as alpha times x1 comma x2 is equal to alpha times x1 comma alpha times x2. So this will simply mean that if you have an x1 x2 in the space x1 x2, that is R2, so what would it mean to say to multiply this by say 2? It simply means that you have a vector that is doubled. So this will be our 2x1 comma 2x2, which is same as 2 times x1 comma x2. That's the geometry behind it. So if you have a minus 2 times x1 comma x2, you will have the vector doubled in the opposite direction. So that's the scalar multiplication and vector addition in the space R2. This can be extended to Rn. All you need to do is to add a few more coordinates to x1 and x2 to get up to xn. There are plenty of other examples of vector spaces. Another example is something called as Rx, which is nothing but the set of all polynomials with coefficients from the set of real numbers. To write it set theoretically, I can write it this way: a0 plus a1x plus so on up to an x raised to n, where all these ai's are taken from the set of real numbers and n belong to the set of natural number union 0, which means that you can have n is equal to 0 as well. How would you add two polynomials? What does it mean to add two polynomials? So you can define addition in Rx as follows. So if you take two polynomials, say px, which is say a0 plus a1x plus so on up to an x raised to n, and say if you have another polynomial qx, which is say b0 plus b1x plus so on up to, okay, you can probably go further because there is no restriction on the degree. So you can have up to bm x raised to m, where m is greater than n. So in such a case, how would you define the vector addition here? So what we will do is we will simply collect the coefficients with the same degree, coefficients attached to these variables with the same degree. So you can have a0 plus b0 plus a1 plus b1 x plus an plus bn x plus, now you don't have any an terms left here, so what we will do is we simply have the bm terms. This is how you add two polynomials. So the vector addition here will mean this. How would you multiply a polynomial with a scalar? So if you have a px, which is a0 plus a1x plus so on up to anx raised to n, then alpha dot px will simply mean alpha a0 plus alpha a1x plus so on up to alpha an x raised to n. So you can see that these two operations defined on this set Rx will satisfy all the 10 conditions that we just saw. Okay, let me give you a few more examples of vector spaces. The third example is m cross n R. This is nothing but the set of all matrices aij of order m cross n, where all these aij's are taken from the set of real numbers. For example, you can have m2 cross 2R, which is nothing but the set of all 2 cross 2 matrices. So I can write it in a elaborate way because it's simply 2 cross 2, and all these a11, a12, a22, a21, they're all from the set of real numbers. That's the reason you use the notation R over here. You can also denote it by simply m2R. So if I'm not writing it as 2 cross 2, it would simply mean, if I'm simply writing it as m2R, it would simply mean that this will contain all 2 cross 2 matrices. And the usual matrix addition, that is a11, a12, a22, a21, a22 plus, if you have say b11, b12, b21, b22, which is simply the addition of the corresponding elements, a11 plus b11, a12 plus b12, a21 plus b21, and a22 plus b22. This will be the addition in m2R. And what would scalar multiplication mean over here? So if you have an alpha times a11, a12, a21, a22, it would be simply alpha times a11, alpha times a12, alpha times a21, alpha times a22. As I said, for a physicist, vectors are represented by these arrows. Now you tell me how you can represent such matrices with the help of these arrows. How can you represent the polynomials with the help of arrows? Okay, let me give you one more example of a vector space. This would be the fourth example of a vector space, and it is fxr. What do you mean by fxr? It is nothing but the set of all functions f from a non-empty set x to R. When I say set of all functions, they literally mean all functions, whether continuous, discontinuous, injective, bijective, surjective, whether it is nothing among these, even if they are simply functions satisfying none of the properties, all of them are included in this space. So obviously there will be infinitely many such functions in this space. But how would you define a vector addition? How would you define scalar multiplication? Can these functions be called as vectors? Of course, yes, if this set qualifies to be a vector space. And for this, it will need a proper definition of vector addition as well as scalar multiplication. So what would vector addition mean in this case? So how would you define vector addition? So what does it mean to add two functions, f plus g? So f plus g, what would this mean? So I can define plus in fxr as follows. So whenever I have two functions f and g belonging to fxr, I'll have to define f plus g as a function from x to r as whenever it acts on any element in this space, of course its output has to be in this space. So f plus g, so x is over here, and f plus g of x has to be a real number. So how would it look like? So it would be simply fx plus gx. We know that fx is nothing but a real number because f is a function from x to r, and hence fx has to be in the set of real numbers. G is a function from x to r, and hence gx has to be in the set of real numbers. That is, fx and gx are real numbers, and real numbers can be added. Okay, so this makes sense, and it's a little confusing, but still this addition is simply the usual addition, and this addition is the vector addition. Please remember that. Okay, we can also define scalar multiplication. This is very easy in fxr as follows. So if you have any f belonging to fxr, I can define my alpha f. Okay, I should write it. I can define alpha dot f as again a new function from x to r as alpha dot f. This is simply a notation. It's a notation for the new function, and whenever alpha f acts on any element x, of course its output has to be in the set of real numbers. That is alpha f of x. So what would this mean? It would simply mean alpha dot f of x, because we know that f is a function from x to r, and hence fx is going to be a real number. alpha is also a real number, and hence alpha times fx is also a real number. Okay, so that gives me the definition for scalar multiplication as well. So you can again check that this vector addition, sorry, I used an eraser, this vector addition and the scalar multiplication will satisfy those 10 properties that we just discussed. You can verify it. Okay, now let's look at a counter example. Let us think of a set which cannot be qualified as a vector space. Okay, let's make use of this fxr. What would happen if I choose any set y instead of this instead of the set of real numbers? Why did I go only for the set of real numbers here as my codomain? So what would fxy mean? Fxy will simply mean the set of all functions from x to y, where x is any set, also y is any set. How can you define f plus g? Of course, we will need our f plus g as a function from x to y again, which means that whenever you have an x in the domain, the output, that is f plus g of x, should be in the codomain. So we can make use of the previous example. We had f plus g of x as fx plus gx. Fx plus gx makes sense because fx is a real number, gx is also a real number, and real number plus real number makes sense. But here, can fx plus gx make sense? You know that if f is a function from x to y, then fx is an element from y. G, if it is a function from x to y, then gx is also an element of y. So now fx and gx are elements of y. And what do we know about y? Y is any set. Any set means it can be a set of all weeks, set of all mangoes, set of all birds in the sky. It can be anything. It does not make sense to write any object plus any object. You can add numbers, we know that, and that is the reason we used R as our codomain. So we see that fx plus gx does not make sense provided there is a concept of distance or concept of addition defined on y. So this cannot be qualified as a vector space, and hence we have a counter example of a vector space. So we can produce plenty of examples of vector spaces as well as sets that cannot be qualified as vector spaces. So that's it for now. Thank you.